Okay, so now we have finished off the guest lectures, including my own guest lecture, I guess. So now it's time to go back to the other part of the course. I mean, of course, the guest lectures are there to support your choice of the third part of the project, and also to introduce you to, it's an integral part of the course, so there will be questions about this on the exams and so forth. So it's really a part of the course. That's what I'm trying to say. But now we'll get back to where we ended before the guest lectures, and it has to do with retransmission protocols, ARQ protocols. We talked about the basic first protocol last time, called stop and wait. We also talked about go back N to some degree. We will finish off go back N today and talk a little bit about selective repeat, what are the pros and cons with these different things. Okay, so a short review. So what we want to do is to provide a service which provides transmission of packets or frames, reliable in the sense that packets are delivered in order without errors, regardless if there are errors in the layer below us. So to keep track of everything here, we will use something called sliding windows to keep track of the transmitted and received packets. So sequence numbers here, which enumerate the packets, so there is an order of the packets or frames. Okay, so I will use packet and frames interchangeably. It means the same thing. So there is a certain order of this. So it's the first, the second, the third, and the fourth, and so forth. So we can enumerate those. Now, for practical purposes, we want to reuse these sequence numbers. So we assign, say, m bits to the sequence numbers, which means that the highest number we can have, if we start at 0, would be 2 to the power of m minus 1. Okay, so whenever we do arithmetic on sequence numbers here, it's implied that that is modulo 2 to the power of m. So for instance, if we have a 4-bit sequence numbers here, that means that the sequence numbers can be from 0, 1, up to 2m minus 1, which is 15 in this case, right? So the sequence numbers here of the packets could range from 0 to 15, and when we go to 15, we recycle and start over with 0. Okay, and then we have a concept of what's called a window or a send window, and this has a size 8 in this case, which is basically the focus of our attention at this current time. So at the current time, we keep track of 8 of these packets in this infinite sequence of packets. Okay, so these are the packets that we are concerned about at the moment. And how to interpret this is that within the window, which starts here and ends here, so this is the window, we have some packets to the left here. And these are packets that we have already processed at the transmitter side. We have received them from the layer above. We have sent them over the packet. We have received acknowledgements for them. Everything is fine. These have been delivered. Okay, so we don't care about those anymore. Then we have a bunch of packets that we care about at the moment. Some packets, 7, 8, and 9 here, are packets that we have transmitted but have not yet received acknowledgements for. So these are packets which are transmitted but not yet delivered. At least we don't know that at the transmitter side. We aren't sure about the status of these. And then we have a number of empty slots here in the send window, and these are slots for packets which we have not yet received from above. So in this current state here, we have 3 packets which we have received from the layer above, and we have transmitted those. We have space for 5 more packets in our send window. We haven't received those yet. Okay. Then we have 2 state variables, one which is called SF and one which is called SN. And SF is the first, or F for first, I guess, is the first or the oldest outstanding packet. So what is an outstanding packet? Well, an outstanding packet is a packet that we have transmitted but not yet have acknowledged, received an acknowledgement for. Then we have a state variable called Sn, and this points at the slot, an empty slot in the send window, which is the sequence number of the next packet that we will transmit. So we have transmitted packet 7, 8, 9. The next one we will transmit will be 10. Okay. The size of the window is the number of available positions where we can put our packets in. And to the right of the send window, we have future packets which we cannot accept from the upper layer here. So if the send window is full, that we have no empty space here, then the upper layer is blocked. Okay, it cannot request transmission for any new packets. So okay, yeah. And then what happens when SF is equal to Sn? Then by convention, we mean that means that there are no outstanding packets. So the send window is completely empty. We have no packets in transmission at that point in time. Okay. So in go back n, our main idea is the following: is that the receiver is essentially as a stop and wait. So we can think of that as having a receive window size 1. We use a send window which has a size which is greater than 1, and we use cumulative acts, which and I will explain what that means in the next slide. There are many variations of this go back n. So when you read in Furusan, the textbook, you will get one explanation. If you read in another book, you potentially would get another explanation. And if you read on Google, you get the third one. So there is a little bit there is not one single protocol here. However, we will use the version which is described in our book to avoid too much confusion here. In Furusan, go back n is described as a transport layer protocol. That is not go back n is not constrained to be only in the transport layer. It could be also in the data link layer for sure, and then other layers also. So, but if you read it, it will be in the chapter that deals with transport layer. So, but don't take that as that go back n is only in the transport layer. It could be in other layers also. Okay. Now, so the send window for go back n, we use acknowledgements with acknowledgement numbers. So when we get an acknowledgement back from the receiving end, there is a sequence number, or there is a number in that acknowledgement called the ACNO. So the ACNO is the acknowledgement number we get. And then the question is, how should we interpret this ACNO? We use cumulative acts here, which means that an ACK with number ACNO acknowledge all packets which has sequence numbers which is less than ACNO. Okay, so I'll take that one more. If I get ACNO, say 3, that means that I acknowledge all packets with sequence numbers less than 3. So packet 2, 1, 0, and then go back to whatever we had earlier, maybe 15, 14, 13, and so forth. So the following happens, that if the transmitter gets an acknowledgement, it's error-free. If it's erroneous, we just toss it. But if we get an error-free acknowledgement message with acknowledgement number ACNO arrives, then what do? First of all, we ignore the ACK if ACNO is outside the window. So if it's less or equal to SF or greater than SN, we ignore it. So if I get an ACNO which is less than SF, what do we mean by that? That ACK will acknowledge all packets which are to the left of the window. And it doesn't mean anything from us because we have already received acknowledgements for this, so it brings no new information to us. Okay. On the other hand, if the ACNO is greater than SN, what does that mean? Well, it means that it acknowledges something weird here. It acknowledges, for instance, a packet which has not yet been transmitted. So something is wrong here, if that happens. And in that case, we toss it also. If the ACNO is greater than SF and smaller or equal to SN, then we process that. Okay, so here, if the ACNO is in this range, then we process that. Okay. So the thing is to keep track of here is that, you know, which of these acknowledgements actually means something to us. And the acknowledgements that are in this range actually means something to us. If it's to the right here, it's something which is completely bogus. If it's to left of us, it doesn't matter because we already knew that information. Okay, but anyways, if it is within this range, so if it's in the blue range here, or let's do that purple instead. If it's in the purple range here, we need to do something about that. And what do? Well, we put SF, this variable, to ACNO. So if this is the ACNO we get, then what we do is that we move SF to the right and put it down here. So what does that mean? Well, it means basically that we move the left-hand side of the window to the right. So we slide the window. We move it to the right. Okay. Then two things can happen. Either that SF is equal to SN, and that means that all the packets have been acknowledged and there are no remaining outstanding packets. Or it could mean also that SF is less than SN, which means that there is still some packets in transition that we have not yet received acknowledgements for. There are outstanding packets. And this has a consequence. In the first case, we stop whatever timer we had, okay, because there is no more packets to time out. And if we receive, if there's still some packets which are in transmission, then we restart the timer, which means that we reset the timer and start it again. Okay, so we will talk more about the timer and what it means in this lecture. But are there any questions so far? Okay. So the transmitter logic is such that we acknowledge, we process these acknowledgements as we go along, we slide the window if possible, we ignore bad acts. Okay. So to give a small example of what's going on here, so suppose we have 3-bit sequence numbers and we have a size 7 window, and then we transmit some packets. In the beginning state, SF is equal to SN, which means that there is no packets in transmission. Then we get a request from the layer above, and then we put in that packet as sequence number 0. Okay, so we store the packet here in the send window, and then we transmit packet 0 over the channel. Everything goes well, so that's accepted by the receiver. And then the receiver sends an acknowledgement. And it sends an acknowledgement which acknowledges packet 0 and all earlier packet. So what should be the ACNO of that? What should be the number? Well, the number should be 1, because that acknowledges all packets which are less than 1. Well, it has a sequence number which is less than 1, 0 and so forth, right? And then this ACNO goes over here, and this is then processed by the receiver. And the receiver says, okay, so oops, what happened? Okay. So the receiver says, okay, I get an acknowledgement with ACNO 1, which means that it acknowledges packet 0, this one. So it puts SF now equal to ACNO, that is, puts SF equals to 1, slide the window. Okay. And in this case, there are no outstanding packets anymore, and we stop the timer because there is no need for a timeout now. We don't have any packets in transmission. Okay, and then we go on, and then there is a new request from the layer above. We get a new packet. This is called packet number 1. It's transmitted over the channel. It's delivered. It's acknowledged, and since there is packet number 1, the acknowledgement number is 2. It acknowledged packets 1 and 0 and so forth. This acknowledgement is lost. At the receiving end, we get a new request, and then we transmit packet number 2. So packet number 2 goes over the channel here. It's received well. So then packet number 2 is acknowledged, which means that the ACNO is 3. we get a new request from this, and from the layer above, we put in packet number 3 here, we transmit packet number 3. And then, at the receiving end, what happens here? At this point in time, the receiver has transmitted packet 1, 2, 3, which are not yet acknowledged. Right? So the receiver has no idea about the status of these packets, but then receives an acknowledgement with acknowledgement number 3 at this point in time. That means that the receiver knows that certain packets have been received correctly, namely packets who have sequence number less than 3. Which are those? Well, it's packet number 2 and packet number 1. So we can slide the window and just keep packet number 3, because packet number 3 has not yet been acknowledged. So we slide the window and then we're in this state. Okay. Packet number 3 has already been transmitted, and the acknowledgement for packet number 3 arrives here, and then we can slide the window, and here we can also stop the timer because there is no more packets that needs to be timed out. Okay. Questions on this? Is the logic pretty clear to you guys now? Okay, so the idea is that we use cumulative acknowledgements, meaning that the ACNO that we get acknowledge not only one packet, but all packets which have a sequence number which is less than the ACNO. So this packet here, when it arrives here, acknowledge not only packet number 2, but also packet number 1. Packet number 0 for that matter also, but that is of no consequence for us in this case. And the beauty of this is that we can lose acknowledgements without disaster happening. Right? We have some robustness against lost acts with this idea. Okay, so now we have looked at the case where we lose acts. Let's look at the case when we actually lose packets also. What is going to happen then? When it comes to retransmissions here, then again, there are different versions of this. So if you read the literature, you might have other rules for doing retransmissions. But in the Fursan version of this, we use a single timer. And when the timer expires, we do retransmissions. So retransmissions are only triggered by timeouts. Nothing else. Okay. So, and when the timer expires, then we retransmit all outstanding packets. Okay. So, if we're in a situation like this, and the timer expires for some reason, we then transmit packet 7, 8, 9, 10. We retransmit all of these, because we are uncertain about which of these packets have arrived or not. And the safe thing to do then is to retransmit all of them. Okay. So an example of this, it's a little bit small perhaps, but let's go through this. So here again, we start by having an empty send window. We get a request and then we fill in packet number 0. We transmit packet number 0, we get an acknowledgement, and then we slide the window. So here's a successful sequence of transmissions and acknowledgement. Then we get a new packet here, packet number 1. We put that in the send window, and we send it, and we lose it. Okay, so here we lose the packet. Then say that we get a new packet, packet number 2. We transmit packet number 2. Packet number 2 arrives. Okay, so what is done here at the receiving end? The problem of the receiver here is that it only has space for one packet. And it's waiting for packet number 1 here. What did it get? Well, it got packet number 2. That is of no use for the receiver. The receiver wants packet number 1, not packet number 2. You want packet number 2 only after receiving packet number 1. It has no way to store packet number 1, so it tossed that. It discards that. Okay. So the packet is discarded. Of course, it cannot be delivered, right? Because the application, the layer above it, should have packets in order. So that's not allowed. Has no way to store it. So what do? Well, you have to discard it. Okay. But then it sends back in an acknowledgement of what it wants. It sends back ACK1 here because that's what it did previously. And by sending the ACK back 1 here is like insisting, okay, you send me something that I don't want. I want ACK. We can also interpret this as I request packet number 1 when you send back an ACK1 here. That's another way to interpret that. Okay, but the receiver is still unaware of this. So it happily keeps on transmitting packets here, you know, packet number 2 and packet number 3. Even when it gets packet number 3, that is discarded. The packet is discarded because it's out of order. We still want packet number 1, right, at the receiver. We don't want packet number 3. We don't want packet number 2. So that's discarded. We transmit them back ACK here. And we keep on doing this. You know, it seems stupid, but we keep on doing this until the timer timeouts. There is a timeout here. So at the time of the timeout, the receiver says, uh-oh, something must have gone wrong here. So what do we do then? Well, the transmitter looks in its send window and says, okay, I have packet 1, 2, 3 here, there is something wrong here. So I'll just retransmit all of these. So packet number 1, packet number 2, and packet number 3. And in this case, all of them happens to receive perfectly. And they are acknowledged, and at the end of the day, we empty the send window. Okay. And then we're back to where we started. Okay. So the important thing here is that when we lose a frame, eventually this triggers a retransmission. And that retransmission is triggered by the timeout. At the time of the timeout, the transmitter transmits the outstanding packets, which is more packets potentially than those who have not arrived at the receiver. But the transmitter knows that the receiver had to throw those away. So the transmitter has to send them again. There is no other way. Questions? Yes?
Let's say we lose packet 3. Do we only retransmit packet 3 in that case? Because you have asked for the packets.
So if we lose packet number 3 here,
yeah.
In addition to packet number 1, you mean? Or
No, let's say packet 1 and packet 2 are nice.
Yeah, so then those would be then acknowledged, and assuming that we don't lose the acknowledgements here, then we would slide the window so that packet number 1 and packet number 2 are released from the window. So when we get a timeout, it's only 3 that we retransmit. So the idea is that at timeout, you retransmit the outstanding packets, whatever they might be, right? That's a good question. Anything else? No. Okay. So there is a state diagram of this also. So if you have a hard time following the verbal or step-by-step explanation of this, you can look at these state diagrams. There is sometimes also a little bit difficult to read. So when I'm trying to understand a protocol, what I try to do then is to read the description of it. What is the main idea? And then I look at if there is a flow chart, I look at that. And if there is a state diagram, I look at that. And together, all of these 3 components or 4 components gives me an understanding of what's going on. And then draw a couple of examples to figure out what's going on, right? So I don't know what you think is the easiest way to do, but these are different equivalent descriptions of the same thing. So pick the one that you're most comfortable with. Okay. So this is the receiver. So it's a little bit more complicated than stop and wait. But anyway, so let's look a little bit about these retransmissions, because obviously what we would like to do is to somehow be efficient. It's if we then look at the key things when designing this is to select a window size and a timeout. These are the two things that tells me basically that governs how many packets are retransmitted when there is a frame error. So if we start with the simplest case when there is no errors ever, right? So for maximum efficiency, when we have error-free transmission, what should we do then? Well, we should select then the send window size to be large enough to avoid idle medium. Okay. And the timeout should be larger than the round trip time to avoid unnecessary retransmissions. So if we draw a timing diagram of this, oof, that was unpleasant. I don't dare to use that one anymore. So we have a transmitter here and a receiver timeline. So remember that when we start everything here, suppose we transmit the frame and it has a certain duration, like this. And the duration of a frame is what we call TF. Okay. Then this is transmitted over the channel. There is some propagation delay. And then there is some processing delay. And then there is an acknowledgement going back like this. And there is some processing delay. And at this point in time, in stop and wait, we are ready to transmit the next packet. Okay. And the time between the initiation of the transfer to when the acknowledgement has been received and processed, this is called the reaction time or turnaround round trip time. Okay, so this is stop and wait, if you like, that we transmit one frame and wait until it has been acknowledged, and then we're ready to transmit the next frame. If the frame or the acknowledgement is lost, there is a timeout, and then we transmit the next packet. Now, in go back N, we are not waiting for the acknowledgement of this packet until we transmit the next packet. So we can transmit the next packet here, say, and we can transmit, we can continue with these packets, hey. Like this, okay? So at any given point in time, the maximum number of packets that we can have in the send window determines how many packets we can, at the most, have in transmission at the same time. So if everything goes well, the acknowledgement for this packet is arrived and processed at this time, and then we can slide the window, meaning that we can forget about this packet and just keep the blue ones, right? So anyways, what I'm trying to say here is that the send window needs to be large enough so that we can continuously keep on transmitting packets. Because if it's too small, for instance, it only holds 3 packets, then we can transmit this one, and this one, but we cannot transmit this one, which means that we will be idle. We will not be using the channel to its maximum ability. Okay? So we want to keep the send window large enough. Okay? And if there are no errors, we need to have, in this case, 1, 2, 3, 4, 5 packets in the send window. So the send window size is determined by the turnaround time divided by the frame size. That is the minimum size of the send window we would like to use. Like this. Okay. Error-free now. So forget about errors. So this is at least we want a window size this big. Now, if it's not an integer here, we round up. Okay, so this means round up. This, these brackets means this. Okay. So in this case, we T0 divided by Tf is 4 point something, and then we round it up to 5. Okay. Now, how about timeout? If we have error-free, it doesn't matter what we choose the timeout to, because there will be no retransmissions ever, right? But remember now, if we have errors, we would like the timeout to be as small as possible, but not smaller than this. So what do I mean by that? So if we time out before T0, then we will force retransmissions, regardless if these transmissions were correct or not. So it never makes sense to make the timeout less than the turnaround time. Okay, so the timeout, we want that to be larger or equal to T0, always, right? And so one choice for timeout in this case would be to set it to C, the size of the send window times Tf, because this is greater than T0. Right. So we can select the timeout in this case to be this. Right. Because then we give ourselves the, if we look at this packet, we give ourselves the time for this to be processed before it times out. Okay? And if it's processed correctly here, the window would slide, at this point in time it would slide to forget about this, and then the timer, when we slide, will be reset. Okay? It will be reset actually starting from this time, and then there will be another timeout. Okay? So it's just the way the protocol works in this case. So the timeout should be larger than the turnaround time, but we also want it to make relatively small. And the reason for this is that if we make the timeout very, very long, then if the first packet here is lost, it will be triggered a retransmission way back here, which means that we have a send window that spans the number of outstanding packets then is quite large. Okay. So we want the timeout to be also small. So this is a reasonable choice of these two things, the send window size and the timeout. There are other combinations one could also think about, but you know, to keep things simple, let's do this. It's not a completely stupid design, at least. Any questions? In my experience, this is a little bit of the difficulty in Go backend, to figure out, okay, what is the relationship between the timeout, the send window, what should we do in different cases, and so forth, right? So if you're confused now, that's okay. If you're not confused now, maybe you should be, right? Because then maybe you should read up on this until you have a clear understanding of what's going on. Okay. Now, if there are errors here, for instance, if we lose this acknowledgement here, even though that this is okay, and if we lose this one, we would trigger a retransmission of all these frames at this point in time, when there is a timeout. So if we want to be robust against errors in the acknowledgement, what we want to do then is to increase the size of the window with some number, a. Like if a is equal to 1, that means that we can tolerate one lost ACK. If a is equal to 2, it means we can lose 2 consecutive ACKs without any problems, right? And then we should move the timeout also to take this into account. Okay. So anyways, have a look at this, because I know it's a tricky thing to get your head around the first time you see this. Efficiency, okay? So here, the efficiency of go back in here in the case, okay, well, let's wait with that actually. Let's just talk about efficiency in general. So what is this? Well, we have ARQ protocol, it's in a certain layer. The idea is that we should provide a service. We should provide a service to the layer above us. We should provide error-free transmission of service data units, which is protocol data units in the layer above us. And it should be delivered in sequence without duplications. So the effective data rate of the service, what is that? Okay, so if I'm implementing an ARQ protocol, I'm providing a service to the layer above me. What is the quality of that service in terms of data rate? Well, the layer above it, what data rate does it perceive? Well, it perceives the data rate RF, the effective rate. And that's basically the number of bits in one service data unit, so the payload I get from above, the number of bits of it, and divided by the time it takes to transmit that. Okay. So that's the effective rate that the layer above us see. So if a layer at the layer below us have an effective rate of R, so that's the effective rate I can get from below me, then the efficiency of me, being the ARQ protocol, is the ratio between the rate that I provide and the rate that I got. Okay? The rate I get from below is greater than what I can push up above. If I do nothing, basically the data rate below is what the data rate will be perceived to be above also. But as soon as I do a little bit of processing, it will be less than this. Okay, so maybe this will be clearer on the next slide. This is now weird. It's unsynchronized. So let me do this, and then do this. Okay, here we are. Okay, so we're in this layer. So we're doing ARQ, which means that we transmit packets and we receive the acknowledgements. So this is what we have described now. Go back in or stop and wait or something like that. This is what we do. The layer below us gives us R bits per second. The layer above us perceives a data rate which is the effective rate. And the effective rate has to do with the data rate of its logical channel here. These service data units here consist of NF minus N not bits. So what is NF? Well, NF is the number of bits in the transmitted frames. Out of those, N not bits is headers and stuff like this, which is of no particular use for the layer above us. It doesn't care about the headers. It only cares about its payload. So the useful bits from the layer above is NF minus N0. So these are the payload bits. And then we have an acknowledgement with NA bits here. Questions on that? So what is then the efficiency? Well, for stop and wait, and this is what we looked at last time, we have a reaction time, which is 2 times the processing time and propagation time, plus the time it takes for one frame, plus the acknowledgement frame. So here's when the first bit leaves the transmitter of the data frame. Here's when the last bit leaves. Here's when the first bits arrive. Here's when the last bit arrives. There's some processing time. And then the acknowledgement goes back, the first bit of the acknowledgement and the last bit of the acknowledgement. A little bit of processing of this. And now we're ready to transmit the next packet. So this is the turnaround time or reaction time. So there's a propagation time, frame duration, processing time, acknowledgement time, acknowledgement frame time, propagation time, and some processing time. So if we then look at error-free transmission, which is the best case, what is the effective rate of stop and wait? It's the number of upper layer bits divided by the time it takes to transmit one frame, which is NF minus NO divided by T0. And then if we calculate it, we get to this number. Okay. We will later on look at what happens when we have errors in this also, but that we will do that the next lecture. We won't do that today, so never mind that. Okay. Actually, I was planning to talk a little bit about selective repeat today, but let's postpone that also because we're running out of time. So the next time we will meet each other, we will talk about how to calculate the effective rate when we have errors for stop and wait, for go back in, and also for selective repeat. So selective repeat we haven't talked about yet, so I will present that also on Monday when we meet each other. All right, so have a good weekend, and don't forget to choose your application for the third part of the project. I think that's due today, right? Okay?
Alltså jag har en favorit. Ja, eller alltså, du har en annan. Okej.